Okay, talked about displacements, talked about viewport annotations, talked about the formation scale factor. Okay, let's talk about the results. Get your solution, which is U, and then from that you compute everything else. What do you compute? Well, you actually specified it earlier, but right now we haven't changed that, so we computed everything. So we computed the strains, we computed the stresses. So if you look at the stresses, we can actually see where we have computed them. If we go here to probe values, you can select that, and then you can actually say here probe values. Select from viewport, probe what? The elements. Yeah, sure. You can probe the nodes, for instance, here. And you can see here that you have nodal values. But we don't really compute the stresses at the nodal values directly. We compute them in what's called the integration points. So components, all direction, and then position integration points. I believe this is here by default. So if you now go to an element, you will see that you get 4 values at the S meses at this window here. You get 4 values. That's a hint. It shows you how many integration point this element has when it's fully integrated, which is 4, right? You have 4 Gaussian points here. We talked about it in the course, and also I believe at this stage you should have implemented that yourself. Okay, so once we have we computed the stresses at these integration points. What we do then is, or I mean, we do it if you do it manually, but Abaqus does it for you. You can compute it in the centroid, so you can look here. This is the centroid, and if you just look at this lower left corner here, you can see that it's 27.8567. And now if you change the centroid to element face, you can see that it's the same value because, well, it's integrated over the whole face. So the centroid and the element face are the same. If we had used reduced integration, then the integration point will coincide with the centroid. So you would only get one value. Okay, so what's done then from this is that using the mass matrix, the values are averaged out to the nodes. Okay, that's how we get this nice thing here, this nice plot here. Because what's happening here, if we go now to contour options, and we go to basics, and we have a band, we have this set to banded here. If we change it to quilt and apply, now we will get the actual face stresses. So these are average across the face using integration. And if you go to isosurface and apply, you can see here that you have lines. And the interesting thing here is that if you look from one element to another, there are continuous. So this thing is continuing right across the next element. And the reason for this is that this is these are bilinear elements. So you have several, the stresses are linear across this element. So from one node to another, the stresses are changing. You have actually 4 values inside of this thing. And compare this to a linear triangle, which you wouldn't even have this option. I mean, you would have this option, but it would just be blank because there is no isosurface. It's constant. You will only have the quilt option. Okay, you will only have this one, and it will be across the whole thing the same. But in this case, it's not the same. It's not just one color in this element. There are several. In fact, you can show it here that you have several across this thing. And if you do banded, you can see it even better here. Now, this is of course done discretely, so it's interpreted across this face, and then it continues to the next one. The reason it continues to the next one like this, it's because of the option that is set in result options here. you have set this average elements output at nodes, right? If you deselect this and apply, this is what the results actually look like. If we would plot this element by element, this is what we would get like. This is when you remove the nodal values and just look at the elements. But if you have the mass matrix and you interpolate the values at such that you actually compute the unique nodal values, which is a sort of the best averaging you can do, right? So if you want to average the stress in this node, you have to look at all the neighboring or all the connected nodes. This is what you do with the mass matrix. You look at the connection and you weight or you average it using the weights of each element across this, and that's when you get this, instead of having to live with something like this, right? So why do we even look at it like this? Well, it's interesting from an academic point of view when you want to look at like what's the actual what does the field look like across this element here. It's bilinear. Actually, if you had higher elements, higher degrees of elements, this would look smoother, because the stresses inside of every element would be not be linear, would actually be quadratic. So if you have a bilinear element like this, it's bilinear. This thing. If you have quadratic, then it would be quadratic, and you wouldn't have this huge jump from one element to another, even without the nodal averaging. Yeah, so the nodal averaging sort of gives you a wrong picture of how it looks like. Even worse is when you go into this thing here and you turn on banded and go to continuous, for instance, here, and everything looks smooth, but in reality it's not. It's really like this. You have this, you have these here, and you can see here that across the element edge, you have this jump in the normal, right? If you look at the normal, it isn't smooth, and it becomes smoother if you have a higher element order. And if you, of course, increase the number of elements, then these fields will be even more smoother. Okay, so if you go to banded and you go to continuous, this is a misleading picture of what's going on. It just smooths the values linearly across the elements.